Hello again, everyone. I'm Joe Pryweller, Senior Director of Conference Content for Plastics News. I want to welcome you to this webinar presented by Mantle and organized by Plastics News. In this presentation, Mantle will discuss real-world examples of how manufacturers use metal 3D printing technologies for tooling and explore the current metal 3D printing landscape for injection mold tools. Let me introduce today's presenter. Ethan Raito is Director of Marketing at Mantle. Ethan has extensive experience in technical marketing for design and manufacturing products. He previously ran the technical marketing team at a 3D printing manufacturer focused on volume production. During the course of the webinar, you can ask questions by opening the Q&A icon located at the bottom or the top of your computer screen, and then typing in your question. Your question will be asked in the order that it is received after the presentation portion of the webinar is completed. At this point, let me turn the presentation over to Ethan Raito of Mantle. Ethan, the floor is yours.
Thanks for that introduction, Joe, and thanks to everyone for joining me today. As Joe mentioned, my name is Ethan Raito. Today, we're going to be taking a look at a bunch of different case studies around metal 3D printing, specifically for injection mold tooling. As Joe mentioned, feel free to ask any questions throughout. I'll be sure to answer all those at the end. I also have a bunch of parts with me here today, a bunch of tools that I'm going to be talking about throughout. So be sure to be looking at both my slides as well as the camera as I'm talking about different tools that I'm going to tell you a little bit in depth about. But let's go ahead and get started. Quick agenda. We'll start by talking about how metal 3D printing can address some of the challenges of tooling and discuss some of the current methods as well as some of the previous methods. We'll look at Mantle's specific metal 3D printing technology and spend just a little bit of time talking about how it's different than other attempts. We'll spend most of the time looking at real-world case studies with data on how metal 3D printing is being implemented to produce injection mold tooling. And then, of course, we'll start with questions and answers. As I'm sure many of you know, if you're here today on a plastics webinar, you know that the products that surround us every day are manufactured with precision metal tools with mold toolings, whether it's a plastic part or a metal part or any really sort of part. All those parts are made with precision metal tools. We like to look at this example of the workspace, which maybe many of you are sitting in right now. What would this look like without tooling? There'd be nothing in this room. I even think that these tables probably wouldn't be there because they probably feature some stamping tools or something like that. So the world really revolves and needs tooling. But as I'm sure many of you know, there's a lot of challenges associated with tooling. Whenever we're talking to companies that are producing tooling, they're telling us that it's slow, expensive, and very, very labor intensive. It's not unsurprising to hear 12 weeks to a 6-month lead time to produce your tooling to when you're going into production, which is very, very long. Of course, it's costly, tens to hundreds of thousands of dollars to produce this tooling. So it takes a long time and it's very, very expensive. When it comes to the business side of things, the supply chains and the tariffs, a lot of tools are made overseas, which adds to that cost and lead time and has some really difficult logistics associated with them. And then the number one thing we're always hearing from prospects is this lack of skilled labor, this desire to, I wish we could build more tooling in-house, but there's just no way I'm going to be able to hire more machinists, more tool makers, more people to run my DM machines. And the training someone to get up to speed with this takes 4 to 5 years minimum, and it's just a very, very time-consuming and expensive process. So all in all, we like to look at tooling and say that tooling is a relatively high value, low volume kind of application. And notoriously, 3D printing has really been ideal at high value, low volume applications, whether it's a part for a spaceship or it's an implant that's going to go into someone's knee that's very, very customized. All the parts that 3D printing to date that have been very, very successful have been these very high value parts that are produced in low volume. And tooling is another one of those. You're not producing, hundreds of thousands of tools. You're producing a few tools to produce hundreds of thousands of parts, making it a really, really good application for 3D printing. And 3D printing really presented itself as an ideal solution to all these challenges we just discussed. But to date, it has really been kind of a letdown. When we talk to a lot of companies that have tried metal 3D printing for tooling, they really generally are telling us that they haven't seen a lot of value add outside of conformal cooling. The tooling industry really has some very, very unique needs that standard metal 3D printing technologies was not designed for. In order to meet the needs of tooling, 3D printing has to be incredibly accurate. We go to shops that are talking about tenths, and they're talking about tenths of a thou. So looking at incredibly accurate parts, really like the most precise parts that are probably manufactured today. So 3D printing has to be incredibly accurate. The parts need to be extremely durable and stable so that they're not moving at all during any of the manufacturing process. They have to be able to be produced faster than traditional manufacturing, because if you're not producing it faster than traditional, you're not really adding a lot of value. And the technologies have to be easy to use and to implement. That's really a big one, that, if the technology cannot be implemented into current workflows and be easy to implement, it's going to be very challenging to adopt that. And standard metal 3D printing was really not designed with these needs in mind. The most common method of producing metal parts via metal 3D printing today is this method called powder bed fusion. You may have also heard of it called DMLS, direct metal laser sintering, or SLM, select laser melting, but essentially they're all very similar process that involve building parts up layer by layer in a powder bed by using a laser to selectively melt and sinter metal powder together. So you're going to spread a layer of metal powder, you're going to hit it with a laser selectively to build up that layer, spread another layer, hit it with a laser again. So to date, this has really been the #1 way to produce metal parts with metal 3D printing. There's some advantage of this. You can produce parts in literally just in hours. You can have something in your hands to hold. You can do these extremely complex shapes because you're able to build parts within a powder bed and really have almost infinite geometry, which lends itself very well to conformal cooling. But there's obviously some disadvantages with this as well. The parts require really extensive post-processing to produce the surface finish and accuracies that are required for tooling, meaning that when you get a part off the printer, you're going to need to touch every single surface, either with grinding, EDM, or machining, so it can be usable to have a surface finish and accuracy that are going to be required for tooling. In addition, you have to work with these hazardous loose metal powders that you're going to need some HVAC, you're going to need some special rooms, you're going to need some suits involved to be working with the system. And all in all, it's relatively difficult to use to get a stable part out of these processes. So to date, most of the parts that are being produced for tooling with laser powder bed fusion or DMLS technologies look like what you're seeing on the right? They feature incredibly complex conformal cooling, because really the only way to justify this process that requires so much post-processing and so much added cost and lead time is to produce something like this, where you're outweighing those disadvantages with an intense advantage of conformal cooling. So really, because of that, extensive post-processing, we're looking at some DMLS parts here on the right, has really limited the applications of traditional metal 3D printing, because you're really only sufficing this very beginning process of the tool building process. If you're familiar with tool building, which I'm sure many of you are, there's a lot of steps involved, and really traditional metal 3D printing technologies only really suffice those first couple steps, maybe the soft milling step, if even. The rest of the process is still left the same because of how much work needs to be done. So really, we saw that DMLS parts or powder bed fusion parts are really only used for extensive conformal cooling applications, and nothing really outside of that. So at Mantle, we kind of saw the current market of tooling, the challenges involved, the lead times, the cost, the lack of skilled labor. We saw the current offering that existed with metal 3D printing and the challenges that traditional 3D printing had with meeting those needs of tooling. And we really saw an opportunity to design the only 3D printer that's designed specifically for tooling. Tooling is the only application we do here at Mantle. We don't build machine parts. We don't build parts for airplanes. The only application we do at Mantle is precision tooling, and specifically injection mold tooling today. So I have a bunch of tools we'll look at later on, and I'll explain to you a little bit about how our process works and what makes it different. But I just want you to know that from the first day, we really designed our technology to meet those needs that injection mold industry needs. We have a pretty different approach to metal 3D printing than those traditional laser-based approaches we just looked at. We actually start with a metal paste. It's a flowable metal paste, similar to the toothpaste you have in your bathroom and you probably used this morning. But we mix, our paste is a combination of metal powder mixed with some binder and some solvents. That solvent allows this that metal powder to flow in a way that is very safe and flowable without needing to be heated. So our feedstock it comes in a tube, and it's a paste material that is very easy to flow. That's a combination of that metal powder, that binder, and that solvent. The first step in our process is we're going to print it. We're printing it very similarly to an FDM printer or an FFF printer that you may have seen. You could buy one on Amazon now for a couple $100s. We're just extruding material through a nozzle. In our situation, we're not even heating that material. We're simply pumping it because that solvent allows that material to flow and simply be extruded through material. So every single layer, we're going to print that material. We're going to come through and dry that material. Here, we're removing the solvent from that paste, and we're firming up the material a little bit, kind of into a dense foam. This allows the particles to kind of settle down a little bit. It densifies the material a little bit, but mostly we're removing the solvent here and turning it from a paste, like a toothpaste, into a dense foam. Why that's so critical for us is because the next step here is going to be we're actually going to machine that. So we're building our printer inside of an existing RoboDrill style CNC. We're going to come through with 10 different cutting tools, and we're going to machine and refine that shape, which is why when you look at our tools, you don't see layer lines like you would with other technologies. You see feature details that are very, very, very precise, some tiny features that would have been impossible to produce by simply just extruding material. So it's a hybrid approach where we're printing, drying, and shaping, and this is going to happen every single layer. So every single layer is going to be milled flat and have some contour milling done every 10 layers to refine that shape and produce these really, really nice looking parts. What comes off the printer we call a green part. It's still a combination of metal powder that's only being held together with some binder, but we're going to go ahead and put it into a furnace to do a sintering process. You can kind of think of a clay pot. You're gonna form it in a soft state. You're gonna put it into your kiln, and now it's gonna come, a hard, dense material. Here we're putting our green bodies into a furnace. That furnace is gonna get just below the melting temperature of the material. In this case, an H13 tool steel. It's gonna sinter the part, and the resulting part is gonna be a dense, strong tool steel. So you can hear that. But what comes out is 97% and above dense. It's isotropic, and you're not seeing residual stresses or anything like that in the part. They're very, very stable. Just have a couple videos of this actually happening in the printer so you can see we're laying down that paste material, layer by layer. We're going to come through after that. We're going to dry that material to firm it up, to remove those solvents, to allow it to really densify a little bit. And then we're going to come through with our different cutting tools and actually refine that shape. We're going to remove any layer lines that may have happened. And we're also going to actually even add in some features that may have been too small for us to print. Our smallest cutting tool is a 6 thou ball and mill, so we can do some really, really small feature details, some features that really would be impossible to produce without EDM technology traditionally. Afterwards, it's a little harder to get a camera into a high temperature furnace, so it's an animation here, but you're just going to put your parts into the furnace. It's going to run for 24 to 36 hours, and now it's going to come a dense, strong metal part. So, the result of this technology is we designed it to really deliver the features and the accuracy and the surface finish that's required for the injection mold tooling industry. So surface finish 1 to 3 micron RA, that's a Charmy 26 or a D2 surface finish, similar to what you'd get from a Synchro EDM process. Let me see. I don't know how well this is coming across on the screen, these parts here, but you're not going to see any layer lines. Often when we show these parts to people at trade shows or they come by the office, they can't believe that they're printed because you're not seeing any of those layer lines or anything like that you would see on a traditional printed part. Accuracy, we're able to hold a 1 thou tolerance per inch. The reason that's going to scale per inch is because we're losing our tolerance in the furnace. As the part's shrinking about 9% in the furnace, how precisely can we predict that shrinkage? We've really, really dialed that in with our paste and our technology to the point we're able to hold a 1 thou per inch tolerance. So on a 2-inch part, that'd be plus or minus 2 thou. Produce really, really fine features as small as a 3 thou radius on features. You have that ability to do things like conformal cooling. Our materials are stable and durable, industry standard tool steels like H13, P20, soon a 420 stainless steel, and the technology is incredibly easy to use, really producing tool steel. I'm able to produce features and parts that would take, years and years and years of traditional tool making experience really at the push of a button. I like to say I could train anyone on this call to print any of these parts I have on my desk literally in an hour. So really, really easy to use because we know the last thing a tool shop needs is another difficult to use piece of equipment. So that's really, I wanted to tell you just a little bit about the existing landscape of metal 3D printing, a little bit about what Mantle's doing, but I want to spend most of our time today talking about case studies and use cases of how people are actually using this to save cost and time and money. Because yeah, sure, it's great to have a printer that's really accurate and has great surface finish, but if it's going to take 6 months to print a part, or it's going to cost $100,000 to print a part, it's not really going to add any value to this industry. But we'll have a bunch of examples to show how we are adding value, or customers are using this technology to reduce their lead times and reduce their costs. Just a couple examples, some of my favorite examples on the screen here. Well, we're going to talk a lot about a couple of these examples, so I won't spend too much time on these specifically, but generally, 60+% lead time savings, 60+% cost savings, obviously dependent on the application, but for applications that make a bunch of sense. The first example I want to show here is this it's a prototype tool for molding a medical device component during the product development phase. So the parts here needed to be molded in acetal and radel, so they could not have been molded in an aluminum tool like a lot of people would have liked to during that prototyping stage. Radel was molded at 38,000 PSI, had a high melt temperature, and the mold was actually heated as well. Acetal was emitting this corrosive gas during molding, which would have made aluminum not acceptable. So they needed to be able to use these tool steel production materials during this initial prototyping, and for them also to do these late stage trials, since they were trying to bring a new product to market here, this medical device company was. So they went ahead and printed these tools. I unfortunately don't have these tools with me today on their Mantle machine. They printed them in their P20 material. It took about 62 hours to print these two inserts. They went in the furnace for about 36 hours and total finishing time of 24 hours. All they had to do was add the ejector pins afterwards. I believe they printed in a pilot hole, they fed the wire and did wire EDM, and they tapped some mounting holes and ground the outside to fit it into the base. So in just 8 calendar days, they were able to produce a P20 tool steel mold. Which is pretty incredible to think about, being able to produce a tool steel mold in just 8 calendar days to shoot acetal and radel and mold, hundreds or thousands of parts, no problem. So 122 hours of total fabrication, but only 24 of those hours were active. The printer and the furnace are going to run in the background. They're going to run with no input. So their tool makers are really happy that they only had to do a little bit of finishing. We like to say our technology gets you anywhere from 50 to 90% of the way there. So here they got you over 75% of the way there. All they had to do was a little bit of touch up afterwards, and they were going ahead and they were shooting acetal and radel. Couple key metrics here. Lead time reduced from 7 weeks. They were estimating this would have taken them if they had to outsource this tool, because it featured some synchro EDM work. It would have featured some synchro EDM work that they weren't capable of doing in-house, to just 8 days. Active work down from 148 hours to 24 hours. A 50% cost reduction here. The entire tool was accurate within 1 thou without any additional finishing. All the molding surfaces were left as printed as that D2 finish, and all the molded parts passed all visual and dimensional requirements, so they're able to be used for those late stage trials. And their engineers were able to, they loved knowing that the parts they were getting were coming off of a real production tool to really just de-risk their production as well. This is, when we asked them, unfortunately, we're not able to disclose who this customer is, because, they see this as a big strategic advantage for them. But when we were talking with them about, how would you have made this traditionally? They kind of showed us an Excel spreadsheet along the top here, how this process would have worked traditionally. If you're familiar with the traditional toolmaking process, this is probably not new to you, but they would have had to source material, do all the programming work, do some rough milling to produce the general shape, go ahead and do some wire EDM as well for the ejector pins, do the electrode milling and design for all the synchro EDM work, a lot of synchro EDM, and still have to do that finish grinding and things like that. So with Mantle, again, they printed, they sintered, all they had to do was a little bit of wire EDM for those ejector pins and a little bit of final finishing. So from 7 weeks down to just 8 days, which allowed them to dramatically accelerate their time to market. Another example here, I do have these parts with me here today, is this. This is a plasma cutter shield cap for this company, Hypertherm. Hypertherm is a producer of plasma torches, as well as cutting tools, industrial cutting tools, just in general, used for like cutting up steel and really, really hard to cut things. They had a new design they were bringing to market. They were trying to test out these new components, but these, again, were being molded in a 30% glass-filled PEEK, which is a very, very abrasive, high-temperature material. This thing is so stiff, as you can imagine, because it's PEEK filled with glass fiber. The melt temperature of the material was 720 degrees Fahrenheit. The mold was actually being heated with oil to 355 degrees Fahrenheit. So they wanted to see, aluminum obviously was not going to be an option here for their development tooling. So they looked at Mantle to see, how can we print some H13 tools? Here specifically, they went ahead and printed the slide component. This was printed in H13 tool steel. It is a bit longer of a print because it's a relatively big part for our technology. Took them about 129 hours, so about 5 days of printing. Went in the furnace for a day and a half, but of course, all of that work is completely unattended. It's just going to run in the background, set it up. It's going to run over the weekend, over your holiday. Hopefully you're sitting on the beach while our printer just keeps whirling away and producing parts. After the parts came out of the furnace, they did a little bit of wire EDM to a taper on one side for the slide, and they ground and fitted into the mold base. So ultimately, they were able to deliver an H13 tool in just 2 weeks. So for them, dramatically accelerated the time to produce this tool. Hopefully I'm going to turn off the blur because I feel like it's, yeah. So, they were able to produce all this feature detail, which would have required pretty extensive sinker EDM work. They were able, again, to leave all of that printed, as the 2 slides that were used to mold this, component here. So some key metrics here: 75% lead time reduction compared to, again, they would have had to outsource this tool because of the EDM work that was required. A 75% cost reduction with producing this tool. Again, the part was used with no finishing to feature detail, which is normally what people care about. They were able to leave it as is with that kind of D2 sinker EDM level finish, and they were able to mold that 30% glass-filled PEEK. So you can see the tool actually running here. You can see the slides coming in and closing around that part to form those threaded parts on the outside. So, when we talked to them about how they would have had to produce this part traditionally, you can see pretty extensive process above, which is very similar to what we'll see for pretty much all these tools. Long process with rough milling, electrode milling, and design. All the EDM work that was involved in final finishing, and able to remove all that intermediary steps and just do a little bit of final finishing. So from 8-week lead time, they estimated down to just 2 weeks, from $15,000 to source this externally down to just $3,750 with Mantle. So this is, a great example of using Mantle slides for producing some 30% glass-filled PEEK components. So yeah. Awesome. We'll keep going with some more stories, kind of moving over to the molder side of thing with WESTEC Plastics. WESTEC Plastics is a great customer of ours located in California. They actually just recently received their machine. They've been there for over 50 years in Livermore, California. They provide a wide range of services, everything from DFM. They can do mold flow analysis, mold design and prototyping, and they have a full service in-house tool room, which is where their Mantle machine is sitting today. They have 23 state-of-the-art molding machines ranging from 28 all the way up to 610 tons. They can do real-time monitoring, and they have clean rooms for doing medical molding and other cleanliness sensitive applications, so they can really provide to that whole industry. WESTEC decided to purchase a Mantle machine because they really felt that Mantle was going to allow them to free up their very experienced tool makers to focus on other critical steps that they need to do. WESTEC is similar to a lot of molders that I talked to, where they say, yeah, we have a tool room, but pretty much we only do repair and maintenance because we have a couple tool makers and they don't have time to be building new tools. We'd love to build new tools, but their main job is to keep our presses running. So they feel that Mantle is going to allow them to free up their experienced tool makers to spend more time on those critical repair and maintenance, and only have to do final finishing to tools to get them running, because the Mantle machine is going to do 90% of the work in the background, and then they only have to do a couple hours of finishing, like we've seen to get those inserts actually running. So they feel they'll be able to produce these H13 production ready or production equivalent mold cavities and cores, in some cases just days, which they said compared to outsourcing either domestically or foreign, 10 to 12 weeks when they're outsourcing those tools. Also, of course, reducing the costs. Tammy, who's awesome to work with, the president of WESTEC, says that tooling is the base of our company. Without quality tooling, we can't produce quality parts, but it's getting harder and harder to find quality tool makers. Using Mantle, we can complete up to 70% of the job and have our tool makers handle just the specialized steps that only humans can do. We need to take advantage of this technology so our customers can get a service they can't get anywhere else. Labor obviously is a huge challenge right now in the industry. So the ability to be able to get tools that are almost completely done with little to no input from their tool makers is really, really valuable. And they feel they'll be able to actually produce some more tools through that process. So the example, or the specific example we'll talk about with WESTEC is they were in the process of building a multi-cavity tool, or running a multi-cavity tool for one of their medical device customers. It's to produce this medical component, which we can't talk too much about, but we can talk about the tool. The customer, after the tool was already being built, came back and said, okay, we want to make some changes to the design, which is something that you don't ever want to do. But they came back and said, hold up on the tool build. We want to make some changes. We need to validate these changes. In order to validate those changes, WESTEC was asked, can you please build us a single cavity tool as quickly as possible so we can get some parts run to actually validate this, so we can move forward with the full tool build, the multi-cavity tool build. So WESTEC used Mantle's technology to print these inserts, core and cavity. You can see them going through some final grinding there on the right. But again, able to produce these inserts in just a couple of weeks, 50% cost savings by printing these with Mantle. Total active hours, they estimated that their tool room would have had to spend at least 40 active hours to produce these inserts. They were able to get that down to just 10 hours thanks to using Mantle's technology, because they were able to print this, leave the feature detail as is, and just do a little bit of grinding to finish these inserts. It was a H13 tool. So again, H13 tools in very, very short lead time, and then injected that TPE material. So they're able to provide that customer with that validation, get them running faster, and get them, proceeded with that multi-cavity tool. Another molder, NICOLET Plastics, which is an awesome customer of ours. They are located in Wisconsin. Their motto is really fast, fluid, and flexible. They have a couple of different facilities. They have a very highly cross-trained workforce. They have over 40 presses, between 30 and 610 tons. And their goal really is to, lower costs with competitive lead times and really exceed their customer expectations. They're recently opening up a new facility in Ripon, Wisconsin. It's going to be 54,000 square feet. So it's a big facility. They're going to have up to 40 presses. They're going to have clean rooms so they can satisfy some of those medical device and cleanliness applications. Very, very automated focus, and kind of one of the molders of the future kind of idea. And that's where they're going to be putting their Mantle machine to kind of fit into that and automate some of their tool making processes. They have the same challenges with tooling that almost everyone has that we talk to. Very long lead times, very high costs. Providing prototype or low volume tooling is very, very challenging due to lead time and cost expectations from their customers. And it's very, very hard for them to find and hire experienced tool makers, just because that workforce is drying up and it's just not out there. So they'd love to increase the amount of tooling they're building in-house, but they find that very hard and very, very challenging. The application we'll talk about with NICOLET is this slam latch component. So this is actually a component they build for Gamber Johnson. It's used to allow tablets to be pressed into docking stations. If when you see a police officer on the side of the road and they have their laptop, up on their dashboard, this is the kind of component that is inside of those docking stations that allow that to be docked onto their dashboard. For their customer, Gamber Johnson, being first to market is really, really critical. I guess in the accessory market, when a new model comes out, the first, kind of accessory to hit the market really captures most of the market share. So Gamber Johnson was highly motivated to be that kind of first customer on the market for when a new model of laptop or iPad or any sort of tablet comes out onto the market. This part was going to be molded with a 35% glass-filled nylon. So again, the desire here was to have an H13 tool so that the abrasiveness of the material could withstand thousands, hundreds of thousands of shots, unlike what an aluminum would be able to do. So they went ahead and printed 3 different components here, a core, cavity, and there's actually a vent insert as well that went inside of this little pocket here to allow for some venting to be done. The print time was 150 hours, so about a week for all three inserts. And then all three inserts can go into the furnace together for about 36 hours. After printing was complete, this insert took about 10 hours of final finishing, wire EDM of the ejector pins, and then did some grounding just to fit it into the mold base. So ultimately, they were able to deliver an H13 tool steel mold in just 2 weeks. If you can see some of these features on top here, very, very deep ribbed features that would have required pretty extensive EDM to produce, which really made it a great fit for Mantle, because Mantle was just able to simply print those features right into the part. Some of the key metrics here: reduction of lead time from 6 weeks down to just 2 weeks. So being able to go from, if they were building that tool themselves, because of all the EDM work required, they're estimating 6 weeks down to just 2 weeks, because it only required 12 hours of their toolmaker's time compared to 180 hours of what they estimated traditionally. They were molding thousands of these nylon 6.6 glass-filled components. Tool was used again with no post-processing to feature detail. They were able to leave all that as printed with that D2 surface finish, because for this application, a matte surface finish was totally adequate here. So, looking at these kind of charts again, you can see they're able to cut out really all the steps involved in this tool building process, except for that little bit of final finishing with that ejector pins and with the fitting into the mold base, to go from 180 hours of their toolmaker's time down to just 12 hours, a lead time of 6 weeks down to just 2 weeks to produce H13 tooling. So for NICOLET, Mantle really allows them to produce production H13 tooling in prototype time. So they can produce in a week, in 2 weeks, a H13 tool for their customer in a time that their customer is used to getting, if they're lucky, an aluminum tool. Printing gets them inserts that are 75 to 95% of the way complete with very little to no user interaction. Inserts require just refining of those ejector pins, tapping of water lines, a little bit of grinding, etc. Dramatically reduce tooling lead times even on their production tooling, produce H13 tools in as little as a week, and free up their tool makers again to work on those critical projects like repair and maintenance to keep their presses running, which is really what's most critical for NICOLET. I think with 3D printing, it's really common to talk about 3D printing with reducing lead times and reducing costs. Everyone's always, how much faster can you make it? How much less expensive can you make it? But with this technology, actually, NICOLET is finding that Mantle's allowing them to expand their business and actually open up new revenue opportunities, not just lowering costs and shortening lead times on existing projects. One of the reasons for that is because now they can get involved with their customers earlier in the development stage. Generally, NICOLET was mostly thinking about production. They want to produce millions of parts. They're not taking on those low volume orders. They're not taking on those prototyping orders. Now with Mantle, they can take on those orders, which allows them to get involved earlier in the development stage and ultimately allow them to win that production business further down the line. Similarly, the H13 tools can be used for bridging, so they can offer to their customer, sure, we can produce you a tool in a week or two, and then if you want to keep running it, we can run you, millions of parts. Offer the benefits of conformal cooling to their customers, which is something that they haven't been able to do. Increase their capacity of their tool room to build more tools in-house, which is a strategic advantage for them over some of their competitors, and produce highly complex inserts featuring extensively complex deep ribbed features that would require a lot of EDM work that they traditionally would have had to outsource. On that same note, I want to briefly talk about conformal cooling. I know we talked about conformal cooling earlier with powder bed fusion and some of those laser-based technologies, but conformal cooling is something that, of course, a lot of people are looking at with Mantle's technology, but at a kind of different level, where with traditional conformal cooling applications, you really could only justify it if the volumes were insane and you absolutely needed it and it was going to save you a lot of cost. Now conformal cooling, it can be justified at a much more reasonable scale because you're already reducing cost and lead time with this technology. That why not just throw in some conformal cooling anyways, because you're already saving time and cost. That why not take advantage of that as well. This insert here, which I have on my desk, features some pretty complex conformal cooling all throughout. I just realized that I accidentally took out the slide that showed that. I'll have to show it to you guys later, but really, really extensive and complex conformal cooling in this insert here. Reduce the cycle time by over 25%. Of course, they were still saving costs and lead time here by 25% of the active manufacturing hours. And this insert was able to be printed within 2 thou right off the printer. So a lot of that mold detail or the feature detail was left as printed. But again, an insert that may have been totally fine with traditional cooling, but since we're going to print it anyways, why not feature something a little bit more complex anyways, just to get that added benefit of a little bit faster cycle time. Another example here, this is with Westminster Tool and PepsiCo. I have a version here that actually of this. This is actually a blow mold that would fit on for molding the bottom of a Pepsi bottle. As you can imagine, there's more pieces that go up here for forming the rest of the bottle. I wish you could see this part because it has really, really nice surface finish in here. But Pepsi was doing some evaluation of some new bottle designs. They were having some issues with their traditional tooling, specifically related to heat blushing, and they were hoping to see if Mantle's H13 could both help with that heat blushing using conformal cooling, as well as help their tools last a little longer so they can go through all the development molding with the same tool. So they worked with Westminster Tool on some printing with Westminster Tool's printer. In just 9 days, they went from design to completion of this blow mold tool, which is pretty incredible to build a blow mold in just 9 days with H13 tool steel. The tool only required minimal machining, they ground the top and bottom to fit it into the rest of the assembly, and they had to hard mill an outer diameter and an O-ring groove on the bottom that was involved here. But you can see there's a little bit of a spiral in here, not an overly complex design, but better than what traditional cooling would have been to allow for that heat blushing to be removed. You can also see some of the vents that are designed right into there. I don't know how well you can see this, but these kind of venting holes that are able to be printed in and finished to allow for a superior venting of the tool as well. So we're always talking about conformal cooling, but conformal venting is absolutely an application as well to allow you to get to ensure you're getting all those gases out of your tool. I briefly want to talk about the tool steels that we have at Mantle today. Today we have two different tool steels. The first being a P2X, which is a P20 equivalent. The reason we call it P2X is because it actually has a slightly superior corrosion and abrasion resistance to a standard P20. But again, it's fully compatible with standard tooling operations like grinding, milling, machining, welding, EDM. But with that little bit of superior corrosion and abrasion resistance. We also have an H13 tool steel, which is actually the more popular of our two tool steels since they're going to take the same amount of time to process. They cost the same. So most of our customers say they're going to cost the same and take the same amount of time. I might as well have that higher hardness, get that 42 HRC right out of the furnace, get heat treated up above 50 because they're going to get it in the same amount of time anyways. But again, our H13 tool steel fully compatible with traditional finishing. I have an example here of just a sample. You can see, able to hold, 7/10 flatness is what we've seen, able to do all that, machining, grinding, EDM, any of those processes that you need to do to your tool, and very, very durable materials as well. One example I really like to talk about when talking about our tool steels and the durability of our materials is this example with Tessie Plastics. They wanted to evaluate Mantle's materials. They wanted to see, okay, is this legit? Is it as strong as our traditional materials? Is it going to last the same as our materials? Or is this just a prototyping thing? So what Tessie Plastics did is they were running a 32 cavity tool that was used to mold these screws. This is actually the screw that goes into your deodorant stick. So, this would go up into the middle of your stick, you twist it, and it would advance your deodorant. I believe actually they stopped running this tool during COVID because people were not buying as much deodorant since they weren't leaving the house. And when they went to bring the tool back online when COVID was over, they said, let's evaluate Mantle now. We have the tool, off the press. Let's swap out some inserts for Mantle inserts and see how they perform. They took out 3 of the traditional S7 inserts. They replaced 1 with Mantle H13. They replaced 1 with Mantle P20, and they replaced 1 with a traditionally fabricated machined S7 material. Very happy to say that after over 1.65 million cycles, this tool is still running, and they've seen no unexpected signs of wear on the Mantle printed tool. The tool also has some S7 shutoffs on it, so a harder material actually shutting off on this insert. So no signs of unexpected wear, and they were able to actually produce these weeks faster than the S7 one that they had machined. So this is a great example of just the durability. This is for forming, the bottom of this kind of cap here, but weeks faster to produce these inserts, and they're still running, over 1.65 million cycles. We email them every couple of months for asking for an update. They say, yep, they're still running, no signs of wear. So people always think about 3D printing of tooling as prototyping, but absolutely you can do these high volume applications as well. This is a really nice insert for testing plastics. As I was mentioning, our tool steels are fully compatible with traditional toolmaking operations. An ideal application for us is you leave all the molded geometry as is. You're gonna do a little bit of grinding, a little bit of wire EDM just for your ejector pins, but you're not having to do extensive processing to it. But important to know that if you need to, you absolutely can. You can do your machining, your drilling, your tapping. You can do wire and sinker EDM to the part to refine features if you need to. You can polish. We've been able to polish up to an A2 finish without any signs of pitting. So if you need to get that kind of mirror finish on your part, you can polish it to that A2. You can do your texturing the same way you would do with traditional texturing operations, chemical, laser, laser etching, deep chemical etching. And they're going to be able to be repaired the same way a traditional tool will be repaired. Laser, TIG welding, you don't see those halo effects. So you can see an example there. We cut out a notch of a tool, we rolled it up, and then we went across and ground it, and it looks, the same way a traditional tool would look. So if you do need to do repair, absolutely can be done without any changes to your standard operating procedures, which is really, really important to know. One of the first things our customers always ask of us, when they're looking to buy a machine, they say, send us a sample. I want to give it to my machinist and have him work on it and see what he thinks. And, the machinist will come back, with something that looks like this and say, why'd you want me to do this? This is a waste of my time. They say, hey, that was 3D printed steel. Could you tell? And they said, I had no idea. They machined the same way any H13 would machine. I ran all my same settings, all my same standard procedures, and it came out just fine. A good example of this is this application with Fathom, two kind of relatively small inserts that they are putting into a bigger block. This is actually an overmold application for a dental application. Printing here, they saw a 40% lead time reduction. They've reduced operations from 200 hours down to 110. But the reason I'm including this example now is actually because they still had to do quite a bit of EDM work, about 30 hours of EDM work here. You can see some of those features that are in here that are just too small for us to print and machine today. So they went ahead and burned it afterwards. They printed a little bit oversized. Then I went through and polished it up afterwards. So you can see that burning process for some of these really, really thin features that are in here. But even with that, they still reduced the lead time by 40%, operation time from 200 hours down to 110. And most of that came from removing the EDM hours. 100 hours of EDM was traditionally going to be required. They moved that down to just 27 hours. And this was overmolding a 60% glass filled nylon. So really good application here as well. Really just want to wrap up real quick before we go through some Q&As, and I'm happy to take as many questions, comments, etc. We can look at some more content if you want. But about our software, we always get lots of questions about our software, so I wanted to quickly talk about our software. Our software is going to control the whole, it's the brains of the operation, I like to say, but it really makes it incredibly easy to use our technology. You just import your CAD file. It's going to do everything for you. It's going to generate all those additive and subtractive tool paths that literally in just 4 or 5 clicks, your G code is sent to the printer, you hit print, and the thing's going to start working, which makes it incredibly easy to use. That I could really train anyone on the line here in as little as an hour on how to use this technology. That's all I have for right now. I really appreciate all of you joining me today and taking an hour out of your day to join me and talk about metal 3D printing for tooling. You can always feel free to email me if you have any questions, thoughts, comments. I'll go ahead and send out a copy of my slides and the recording, of course. But if you have anything specific, feel free to email me. But thanks so much. And at this point, I'll go ahead and take some questions.